My dear students and the viewers, I welcome you to the class 8 of convection. In this class 8 of convection, we will study about velocity boundary layer in case of internal flow. If you remember, in class number 2, we have studied the same concept of velocity boundary layer. In class number 2, we studied velocity boundary layer, but here we have considered a flow of fluid over a flat plate, right? And hence it can be called as external flow. Okay, and now instead of this flat plate we'll consider a tube or say a circular pipe. So within this pipe, the outer lines here indicates the surface of the pipe. So within this pipe we are making the air or some fluid to flow. Okay, that is what the meaning of internal flow is. So in class number 2, whatever I have shown you, that is for external flow. So in this internal flow we need to study about velocity boundary layer. You can apply the same concept of friction at the surface, whatever we have studied in class number 2. At the surface you have a concept of friction, we have a concept of viscosity, as a result of which there is a velocity, a very much less value of velocity. You can also say it is negligible, almost zero on the surface. And as the distance from the surface increases, velocity will be increased. The point where you will get maximum velocity. Likewise, from all the values of x, at all the value of x, if you go on plotting the points where you will get maximum values of v, by joining all those points we will be getting layer, which is called as boundary layer. So now here, this is flat plate. If I imagine a tube, I'll get one such layer even on the top. So there also velocity will be minimum and it will be maximum at the center of the pipe. That is what has been shown here. So now here, this is the entrance of the pipe. You can imagine that the delivery of a pump has been connected to this pipe. So now I can say there is a uniform velocity with which fluid is entering into this pipe. But at the surface, because of this friction, velocity will be less and it tries to increase. After this boundary layer, after one particular distance, you will get maximum velocity. Similarly, from the other surface also you will get one such point, right? So now as the distance is increased, I mean the length of the pipe is increased, again at one particular point of x, that means at one particular value of length of the pipe, you will get a maximum velocity at the center of the pipe, at the axis of the pipe. This maximum velocity remains same for the further length, it doesn't increase. That means the velocity profile here remains same from this point of x, for this length of x, from here to further this doesn't change, this velocity profile doesn't change. So from this point to further I will call that one as fully developed region, hydrodynamically fully developed region. And from the entrance up to this point where we are getting maximum value of velocity, the least value of x, remember it like this, the least value of x at which you get maximum value of v at the axis of the pipe, till that point from the entrance, it is called as hydrodynamic entrance region. That means from the entrance up to fully developed region, it is hydrodynamic entrance region. And here the whatever the line I have shown in blacking, that is the boundary layer. In flat plate it was only one layer you can find, but here there are two different surfaces, so I will be finding two different layers. So these two black lines are boundary layers, and the distance from this surface up to this point, up to the layer, can be called as boundary layer thickness. So here in general the maximum boundary layer thickness will be from r equals 0 up to r equals capital R. That means from the surface to the axis of the pipe or to the center of the pipe, this will be the maximum thickness, I mean boundary layer thickness that can be achieved. Okay, and here if you can have a clear view, see here the velocity has not reached maximum even at the entrance, even at the center of the pipe. It has, velocity has been increased compared to the entrance region over here. Again it is further increased. So this increase in velocity at the center of the pipe reaches some maximum value and that remains same for further length. So this is, on this basis we will be classifying the entire flow into hydrodynamic entrance region and fully developed region. This is the developing velocity profile, all these three. And this you can say it like fully developed velocity profile. And this is how the velocity profiles will be looking in case of laminar flow. If it is a turbulent flow, you can again imagine similar, you can have similar kind of concept, but the velocity profile, the nature of the profile will be varied. Velocity will be maximum at the entrance, it goes on decreasing and it reaches to some minimum value. From there velocity doesn't change. This is the concept of turbulent flow. This is how velocity varies in turbulent flow, but it is exactly vice versa in laminar flow. And rest of the explanation remains same. The minimum value of x up to which there will be a change in velocity at the axis of the pipe, up to that region, it is called as entrance region or hydrodynamic entrance region. After this we have fully developed region, and from the surface to the point where you will get almost negligible value of velocity, that can be called as sub layer. Okay, since the velocity is very much negligible, slip will be very much less. Since slip is very much less, you can imagine a particular layer of fluid, few layers of fluid over here from the surface up to this point, up to this line, between which the flow will be almost like laminar. Even the entire flow is turbulent, at least at the surface you will get a laminar flow, that is called as laminar sub layer. Okay, and also you need to make a note that at r equals 0 V will be maximum and shear stress will be minimum, and at r is equal to capital R, that is half of the diameter of the pipe, at the surface r equals capital R, in the sense that is at the surface the value of V will be 0 and value of shear stress will be maximum. I repeat over here, at r equals 0 V will be equals V maximum and shear stress will be minimum. You can say it is approximately 0, or you can say it is minimum. Similarly, at r is equal to capital R, V will be 0, okay, that is minimum value, and tau will be maximum. So these are the boundary conditions for this flow of fluid through pipe. So the rest of the concept whatever I have explained here in class number 2, the concept of the Newton's law of viscosity, the concept of delta, that is boundary layer thickness, okay, all these points remain same. You can add the same points even for the explanation of class number 8, that is velocity boundary layer for internal flow. Whatever I have explained here are the key points which has to be added for the explanation from class number 2 in order to have explanation for internal flow. Those are the extra points which you need to add. Fine, thank you.